So we're going to look now at some applications of differential equations. Some of these applications should be at least a little bit familiar, but you might not have studied them in detail. So here we go. First application, interest rates. The simplest thing that I can tell you about interest rates is that they are factors. In fact, my preference would be is instead of calling them interest rate, if they were called interest rate factors. So specifically, what an interest rate is it is a factor that you multiply by the principal to give you the rate that interest is being paid at that moment. So here's an example. Suppose you have $1,000 in an account, and let's suppose that the interest rate is 6% per year. Now, commonly, this would just be called 6%. But to be precise, interest rates have to be per unit time. So what people typically call 6% is actually 6% per year. Sometimes they'll say 6% per annum. So with that principal and this interest rate, then at that particular moment, the interest rate multiplied times the principal gives you the rate at which interest is being added into the account. So now again, you'll notice that that makes this, what they call interest rate, a factor. That's the factor that's being multiplied by the principal to give you the rate that interest is being paid. Okay. Now, at this time, one could make the observation that, okay, well, if the interest is going in there at a rate of $60 per year, then over the course of a year, you might suspect that $60 would be the amount that would go into the account. And of course, now that's not exactly accurate, because as money starts going into the account, this balance goes up, which means that the rate at which money is going to the account actually also goes up. So, not quite as simple as just saying that this is a constant rate. Sometimes this is addressed through ideas of compounding, and we'll talk about that more momentarily. But really, the simplest way to address this situation is just to interpret this definition of an interest rate as an equation. And here it is. An interest rate is the factor that you multiply by the principal in order to get the rate that interest is being paid. Right, so the amount of money that you have in your account, that's the principal, sometimes called the balance in the account. And the time derivative of that tells you how fast that is changing, namely how fast money is being paid into the account. And notice that what we have then, just an interpretation of interest rates, an interpretation of the definition of an interest rate, is that it's a differential equation. In fact, this is a differential equation that you might recognize. This is called the natural growth equation, and this is studied in second semester calculus. So you should know how to solve this equation. If you don't remember how that works, something you definitely need to study up on. And the solutions given an initial condition, the solution is this. Okay, so this initial value problem has that solution. Okay. Now, you can arrive at this conclusion by, again, as I sort of alluded to earlier, taking the idea of simple interest and then applying the idea of continuous compounding, thinking initially about finite compounding periods and then increasing the number of compounding periods and taking a limit as it approaches infinity. But it's really more easily understood and really more naturally understood as just thinking of interest rate as a factor that you multiply by principal to get a rate that interest is being paid, and realize that that's just language describing a differential equation. This is really the most natural interpretation, and it just gives you a differential equation to solve, which is not that hard. Okay. So here's another example related to money. Suppose there's an interest rate R, and in addition to that, you are making your own savings deposits in the amount of S dollars per year, S for savings. then if you look at the two different contributions that are being made to how fast is my balance increasing. On the one hand, the balance is increasing as a result of interest payments, and from the previous page, RB tells you what those interest payments are, the rate that the interest is accumulating. But then in addition to that, we are also making another contribution to the increasing of the balance by way of this savings rate. And altogether then, we have now a new differential equation. And I want to talk quickly about how to solve this differential equation. Now this is a separable differential equation, and you could apply that method to separate this equation and solve it directly. But here's a neat little trick. And the trick is this. Make this substitution. Let Z equal to RB plus S. In other words, the right-hand side of the differential equation. Taking the derivative of both sides, you get that. And now let's ask the question, what can we say about B prime? Well, B prime is the derivative of B. This equation here says that that's equal to RB plus S. And this equation here says that's equal to Z. And let's take a moment to let that settle in. This B prime is exactly Z. So this equation becomes that. And very conveniently, this is a natural growth equation. We know how to solve natural growth equations, and you can then solve for Z directly. And once you know what Z is, then you can solve for what you're actually interested in, which is B. Okay. All right, so it's a neat trick, something to keep in mind. One more example. Here's an example about concentrations and mixings of liquids that have, in this case, salt that's mixed in with the liquid. So here we have a 1,000-gallon tank. It's a full 1,000-gallon tank, and there's water flowing in at a rate of 5 gallons per minute, and then it flows out at the same rate. So in this case, though, the input has a certain concentration of salt, specifically 3 pounds per gallon concentration of salt is the water that's flowing in. Okay, so given that, how can we describe the rate of the changing of the concentration of the water that's in the tank over time? The trick on these is to realize that if you're interested in concentrations, don't try to write a differential equation for concentrations. Concentrations don't add very conveniently. If you have two glasses of water that have the same concentration of salt, if you pour them both into a bucket, the concentrations don't add. You don't get double the concentration. You get some sort of averaging of the concentrations depending on this and that. You know, how much of this liquid, how much of that liquid. What you can write easy differential equations about is the quantity. Quantities do add. If you have a certain quantity of salt and another quantity of salt, when you pour them both into the bucket, the total quantity is just a simple sum. So let's write a differential equation for dq dt, or differential equation for q, and thus try to write down what is dq dt. Well, here's how much water is going in. This is rate of change of the quantity of the volume of water that's going in, and this is the concentration. So this product then is the contribution of salt from the water that's flowing in. Here's the water that's flowing out. It's also 5 gallons per minute, and it is concentrated at, well, whatever the concentration level is for in the tank at that moment. And this is not quite a differential equation because we're taking a derivative of q, and c is a different function, but these are closely related. Specifically, concentration concentration is quantity divided by volume, but volume being 1,000 gallons. So we have here then a differential equation for quantity, and once you have solved for Q of T, then there's your formula for concentration.